In this video, we are going to continue the discussion of the quantum mechanical harmonic oscillator. All right. So in class, we started the discussion with the Schrodinger equation. And so if you remember, the potential energy is written as 1/2 the mass, frequency squared, times the position squared. And we're doing this in the position basis. So we can write out the we can write out the Schrodinger equation as the second derivative of the wave function plus 2m over h bar squared e minus m omega squared over 2 x squared times the wave function, and all of that is equal to 0. Okay, so now we made some unique choices in terms of substitution. X we wrote as by, and then b we wrote down as the square root of h bar over m omega. And lastly, we said that the energy was a reduced energy, which is the total energy divided by h bar omega, which is a good choice because h bar omega is from Planck's equation showing that energy is related to the frequency of the wave. Okay, and what that gave us now is a new equation, a much simpler looking equation of the second derivative plus 2 reduced energy minus y squared times the wave function is equal to 0. Much cleaner. We combined all the constants, got rid of all that stuff, and now we have this nice clean equation where we're going to rewrite things as epsilon naught is the dimensionless energy, and I think I made a mistake in class because y is a dimensionless quantity. Because if we look at b is the square root of h bar over m omega. And if we work this out, this gives us a unit of length. So b is now carrying the length unit with it. Okay, so let's take a look at this differential equation. Let's take a look at the long range limit. So let's say that y squared is much, much bigger than 2 epsilon. Okay, so we're looking at a very long distance. So if that is the case, then our equation reduces to something very simple, where that we've seen before, and we say that this is essentially proportional to e to the minus y squared over 2. Okay, so that's good. So in the end, what we get is a wave function that should have an exponential decay the further and further we get away from the origin. So let's turn this into a real function. So psi is a function of y, is some function of y, e to the minus y squared over 2. So at small y, the h function dominates, and at large y, the exponential dominates. Okay, so now let's put that back into our equation, and so we get something that looks like this. bring down, and I get minus y. Okay. So let me rewrite this to make it a little cleaner. Oh, sorry. Okay. So now let's take the second derivative. The second derivative. Okay, so we do this again. We get the second derivative of h, e to the minus y squared over 2 plus minus y, e to the minus y squared over 2, the first derivative of h. So that's the chain rule on the first term. And on the second term, we now have minus e minus, so minus e to the minus y squared over 2 times h minus y times minus y e to the minus y squared over 2 times h. And then last but not least, we get minus y e to the minus y squared over 2, the first derivative of h. Okay, so now we have all these terms. So let's start combining them together. So if we combine some stuff together, what we get is e to the minus y squared over 2, the second derivative of h with respect to y. If I look at this, let's see, then I can combine the second and the last, and I get minus 2y e to the minus y squared over 2, the first derivative of h. And now combine the third and the fourth term, and I get minus e to the minus y squared over 2 times h minus plus y squared e to the minus y squared over 2 h. Okay, so essentially we now have these four terms. And now we're going to put that back into our Schrodinger equation, our reduced Schrodinger equation. So let's try and write this out without getting too lost. And we essentially have e to the minus y squared over 2, second derivative of h, minus 2y e to the minus y squared over 2, first derivative of h, minus e to the minus y squared over 2 h plus y squared e to the minus y squared over 2 h. So that's just the kinetic energy part. Now we have to add in the second term, this stuff right here. So that's going to be plus 2 epsilon 8 h e to the minus y squared over 2 minus y squared e to the minus y squared over 2 h. So that was the part that is the potential energy of the spring. And all of that is now equal to 0. And so if I look at this, two terms cancel. So essentially this last term here and this term right here, those terms cancel. And what I'm left with now is so here I am right here. I'm left with 0 is equal to e to the minus y squared over 2, second derivative, minus 2y e to the minus y squared over 2, first derivative, minus e to the minus y squared over 2h plus 2 epsilon h e to the minus y squared over 2. So if you notice, each term has an e to the minus y squared over 2. So if we divide that out, we get 0 is equal to the second derivative of this function h minus 2y, the first derivative of the function h, plus 2 epsilon minus 1 times h. So now we have a new polynomial, which is only in terms of the h function. So we got rid of the long-term exponential part of it. And now what we're left with is this new polynomial. And so what we want to do is we want to solve, not polynomial, we've got this new function h. So we want to solve this function h. So we want to solve this second order differential equation. It's got 1 second derivative, it's got a first order derivative. And so in this case, it looks like a polynomial. And so we're going to solve it with a polynomial solution, something called the Frobenius method. And so we're going to say that h is now going to be a polynomial starting with n equals 0, and we have the terms a to the n, y to the n. So in the end, this is going to be a0 plus a1 plus a2 squared, a2y squared, a3y cubed plus dot dot dot, where all of these a's are coefficients. So in the end, they're just numbers. Okay. So we have to figure out what these coefficients are, and we have to find a shape of the polynomial. So we're going to do that. I will actually do that in the next lecture.